So in the previous video I felt I went a little too quickly over the comparison between BSD and BS. So let's just make it clear here. What I'm comparing is two ways to find an element in a data set or a collection of elements. The first way is using the find method from the binary search tree, which we looked at earlier in a previous video. And the second way is to simply use the binary search algorithm, which works on an array of elements that are sorted. So the first comparison, the first distinction is that the binary search tree uses an array, and binary search uses an array. The second thing, and this gives an advantage to the binary search tree, and that's that when you find an element, when you find the element that you're looking for within the tree, then you stop right there and you return that element. You don't carry on further your search to the very end. Whereas in binary search, we always, if you remember, we divided our list in two and kept on doing this until we reached the very end and we had one last element to compare our key to. And when we had low equal to high, these were the 2 pointers, that's the only time when we could return back a key. So even if we had actually found the key before in an earlier comparison, then we would still carry on our division until we would reach this last final element. So this would mean that we would waste a little bit of time. And the final distinction is that, and this gives an advantage to the binary search always guarantees a reduction of the searched items by 2, because you're always dividing the list by 2. So instead of having a big O of n, it's going to become a big O of log n. The operation becomes a big O of log n. In the case of binary search tree, we are not guaranteed this, because in the hypothetical scenario that I drew here, where you have the tree laid out in this manner, and you are looking for an item which happens to be right here, then what you're basically going to do is you're going to be stepping over the entire tree, despite the fact you're actually just going through one subtree or part of the tree and discarding everything to the right. In this case, there's nothing to the right, so you're still stepping over all the elements of the tree, so there's no advantage gained here. Okay, so much for the comparison. Now we can move on to the last function or method we said we're going to be talking about at the very end of our video. So the last function is to remove a key from a certain tree, from a given tree. I mentioned earlier that it was remove min. I was wrong. I confused it with something else. I was talking about actually heaps. But this function that we're going to be talking about is to remove a certain key from a root. So it covers multiple cases, and we're going to see that this method or algorithm actually works by covering every single possible case. So the first case, the most obvious, is that the tree we're passing it is null. There's nothing in the tree, so it's just going to go to this condition and it's going to return a null. The second case, so I'm going through these cases to cover every single possibility. The second case is that the root is a leaf, and for the first 4 cases we're going to assume that the key actually exists in the tree. So if the root is a leaf and the key exists, so the root is actually the key you're looking for, so what's going to happen? You're going to come here and you're directly going to jump through all these 3 conditions. Your key is not going to be less than the root, nor is it going to be greater than the root because it's equal to the root, and you're going to arrive right at this case. So once you're past these, you know that you've found a match. These are all for finding a match. This is to handle the cases where we find a match. And you're going to return the root to the right. So you're going to first check if the root, the left child is null, and you're going to find out that it's truly null. So you're going to return the child to the right, and the child at the right is just going to be null. So you're returning null. So you've removed the entire tree. The tree has, since it was only a root, and that key was in that root, we removed the root and removed the tree, so the tree becomes null. The third case is, what if it was a leaf node that we're trying to remove? So we have a big tree, and the key happens to be at the very end, in a leaf. We're going to be going through the green and the blue cases. The green case is this comparison right here. So we're going to be comparing multiple times, recursively calling the remove function. So first we find that our key is less than the root, for example, then we're going to call the remove function on the left child, and then we find that our key is greater than the root, and so we're going to call the remove function on the right child, and so on and so forth, until at one point we're going to find that our key is at the very end, and it's none of these. So we're going to skip these cases, and we're going to come right here, and we're going to be handled by the blue. And we're going to continue that in the next video.